All right, so today I want to discuss an implementation issue regarding Gaussian processes. Because, for example, if you have a posterior y hat given your data, then, and it is, as you know, we can write it as k star transpose k minus 1y. This is the mean of that, and the covariance is proved to be k star star minus k star transpose inverse of k times k star. So this is your covariance and this is your mean. But the problem is using inversion in the sense of Python, for example, we use np.linearalgebra.inverse. This is the command that you use in Python if you use NumPy library. So this command, or even the pseudo-inverse of that, is prone to inaccuracy. And therefore, the safer method is to use numpy.linearalgebra.solve. So this is a safer method. So how can we use that in order to create a safer and more robust approach, a much faster and scalable, a little bit more scalable approach? So the answer to that question is just apply Cholesky decomposition on K. And what is Cholesky decomposition? I'm sure if you are a financial engineer, if you are a mathematician, if you work on linear algebra and those things, you know that you can always decompose K, your matrix, into L times L transpose. And even the inversion of L is easy, and because something is a lower bound, and so a matrix that is easier, so could have a better and easier and faster way to compute the inversion. So how can we take advantage of that? So what we can do is just we make some variable. First of all, alpha is, when I say alpha, it is k minus 1 inverse of k times y. And now K is LL transpose. And so this becomes L minus T, L inverse transpose, L minus 1, Y. And if you just set M as a variable, you will notice that alpha is just L minus T, inverse of L transpose times M. And then this is just L transpose alpha equal to M. So you can find this, your mu. So your mu is now, your mean is now K star transpose L minus Tm. Remember that this is alpha and this is your mean. So we have calculated the mean without very strange and bad inversion. So now it is computationally more efficient, more accurate, more robust. You can do it in Python very fast. Now let's do it for the covariance as well. So we have done for mean, now we want to do the same trick for the covariance matrix. So what we are gonna do is just write the covariance matrix. It was K star star minus K star transpose inverse of K star. Again, we use another variable. For example, here is beta. And so we can write K beta is equal to K star. And it is obvious that because we know the Cholesky decomposition of K, so we can write LL transpose beta, which is equal to K star. and therefore beta is equal to LL transpose minus 1 K star. And so beta is L minus T L inverse K star. So your covariance is just K star star minus K star transpose. Now instead of beta, you can just put it here, and so this is the way that you put covariance, and you compute it in Python, and so it is not prone to inaccuracy, and you can solve it very quickly and efficiently. And so let's see how can we implement it in Python. Now you know everything, because you know that for example your prior, you want to implement the prior, so L is numpy dot linear algebra dot Cholesky, and you put your kernel is a kernel of test and test plus noise variance times numpy dot I, and I is Python is I of n. So here we say that LL transpose is equal to K plus sigma y squared I, and this is KY. So you can write your prior, F prior, to be the dot product of L, which is n by n matrix, and your normal variable, mp dot random dot normal, and you know that the normal needs a variable which is size. It says that I need n by n sample, and so for example your prior could be n times n sample. For example, you have 100 points of your graph, or 1,000 or 1 million if you want to look like a very, very smooth function. And your samples, for example, you want to generate 10 different functions. So this is this is what you do for a prior. The same thing for posterior. So for posterior, you write that f of posterior in Python, you just write this is mu that I told you, and you reshape it because you want to look like an array, and then mp dot L, and numpy, you use numpy library again, dot random dot normal, size is n and n sample like before. So mu is just L minus 1 K of x and x of test transpose L minus 1 Y, because this is just your M, and you use the fact, I use the fact that if you multiply A and B and make the transpose of that matrix, it is just B transpose A transpose. So I use this fact. So we carry on, and we add L times normal. And so you can implement it in Python very easily. So the algorithm is very straightforward. So I just review it again. Cholesky of K plus sigma y to squared I. You had a variable called alpha, which was L minus T L minus 1y. And we know that the expectation of f of star is just K star transpose alpha. Now use a variable v, L minus 1 K star, and now you have the mean, you have also the variance of f of star. which is equal to k of x star and x star minus v transpose v. And if you want, we can talk about log marginal likelihood because we need it for hyperparameter estimation. If you just want to use some, for example, conjugate gradient descent, and like that. So if we use the log marginal, this is the log marginal likelihood, which is equal to the log, as the name suggests, is just the log of y conditioned on x and theta. And so this is equal to log of your covariance minus 1/2 y minus mu transpose sigma inverse y minus mu. And of course, a term which is constant, and we don't care about it at the end of that. So what we are interested in is, if you just give me your gradient, that's it. I can do whatever I want, gradient descent or anything else. So the gradient of, so derivative of L with respect to theta m is equal to minus y minus mu transpose sigma inverse. You make derivative with respect to theta m. The same thing for other hyperparameters, theta k, for example, which is equal to 1/2 trace of inverse of sigma plus 1/2 y minus mu transpose derivative with respect to theta k, sigma inverse, and finally y minus mu. So you can write, if you're a statistician or if you are a machine learning engineer, you can write your function x star of I, x star and I. So it's just a sum of some functions. You can interpret all of these things very beautifully using these basis functions. For example, in a Hilbert space, you have some basis function. And so it looks like it's a combination of that, a linear combination of them. And alpha here, alpha is just ky inverse y. As I told you, it's just L minus t, L minus 1y. So f bar of x star, I mean the mean of that is k of x star and x. And for noisy formulation of that, it's just k and x, where you add sigma and squared I. And the covariance looks the same. Covariance of f of x star is equal to k of x star and x star minus k of x star and x times k of x and x plus sigma squared I inverse times k of x and x star. So I told you how to implement it in Python. And if you don't know what does this function do, I just explain it. If you write a numpy.linear algebra.solve, for example, L and kernel of x and x of tests. Well, this means that if you have two, for example, this is A and this is Y. Using this numpy function and this method solve, And using this NumPy library linear algebra, you can say that we are solving this. Ax is equal to y. So instead of explicitly writing x is a minus 1y, which is prone to error if you use np.inverse, we use this method, which is highly efficient in terms of computational complexity, robustness. The error is very small because these libraries are tested and they are very robust. For example, if you tell me to write a code to develop a software for Gaussian processes, first of all, I should understand what does the algorithm do, and then and therefore I need to implement it from scratch, completely from scratch. First, you completely derive and write the codes from scratch using the minimum amount of libraries that you need. And after that, after you master that, and you notice that you know the algorithm, you know what is, you get under the hood, you get what is not obvious. So you know the details of that. And after that, because your company is an enterprise and you want it for massive data sets, so it should be robust. So you just ignore your own code and use some libraries such as NumPy, linear algebra, such as SciPy. So any library, for example, EMC, if you are using Markov chain Monte Carlo, some libraries that are robust and tested and used by several companies before, and so you can use it and you don't worry about what happens if there is a bug in the system, because you should always care about the bugs in your enterprise. Otherwise, you can develop everything from scratch. So the point that I always develop everything from scratch is just because, for example, there is something that you cannot find it in any library because it's your own algorithm. It's totally new. It's in, for example, in your paper, and no one has ever seen that. So that's why you should implement it from scratch, and maybe suggest it to some big companies to add it to their packages as well. But after that, after from scratch, you go to use the tested libraries that are very robust, and then because they are robust, you don't care about bugs because they have already been tested by several great software developers and software architects. So everything is efficient in terms of software architecture and those things. So sometimes you should just pick a library in maybe one line or two lines. You just implement the Gaussian processes and learning hyperparameters and write the graphs and everything in just 4 lines. But sometimes you need to work harder and develop it from scratch, which is good if you're an academic researcher and you have your own algorithm, which is no one has seen before. So you are the first person who are going to implement it, and therefore you want to do it from scratch. And so you see that implementing a Gaussian process and learning hyperparameters and training and testing and all of these things and seeing the uncertainty around each point, because each point has a different uncertainty. And using these ideas, you can efficiently implement it in Python. And as I said, everything is just